So thanks a lot, John, for the invitation to be here. I think it's a really nice session. Actually shows a lot about the progress in the field. So it's actually a very exciting field at the moment. And I'll tell you a little bit what we are doing at AstraZeneca. So let's see, how do I get it? Oh. First question you always have around machine learning AI, what is different now compared to before? In the end, I've been in the field for quite a long time now, and we built QSAR model for 15, 20 years with support vector machines and even neural network. And I think there's two things that are different, both what is happening in the field and what's happening outside. In the field, I think uh, uh, that's also two, I think, really exciting development. And for us, it started late 2016. And actually, Marvin was a guest in the lab, and he actually opened our eyes to actually the possibilities, both in the novel molecular design, which I'll be talking today about mainly, and also around synthesis prediction, which also I think is a very interesting, exciting field, and which Marvin covered in his talk. But it's not only in the field that it's actually changed, it's also the environment that changed a lot. And one is the continuous progress of automation, that high throughput screening gets more and more refined. And one example is when we had the new high throughput screening center in Cambridge, we can actually do very big cherry pickings. We then which will allow us to combine that with machine learning for, say, iterative screening and those type of approaches. Also, we're building a chemist automation lab within AstraZeneca that will also hopefully will quickly generate data for training our models. And data generation in itself have, of course, exploded with transcriptomics, next generation sequencing, high throughput conformal microscopy to give much more imaging. And what we hope is, what we believe is that we go from what now are with augmented design, AI helps the chemist to more autonomous design, and hopefully in 5 to 10 years to actually end up in more automatic design. Okay, so, and that's just to show some examples of papers very recently. It's actually illustrated this. It's a very new field, the novel design, and there's several new algorithms presented during the last 1 or 2 years. The GAN type, the encoder type, and what we have been working first in collaboration with Marvin, and then later on worked to refine it and reinforcement of the recurrent neural network. And we also earlier this year wrote a review of various applications of deep learning within the drug discovery process. So what is a neural network and deep learning? So that's just a quick overview. So this is the traditional neural network. You have with an input layer, an output layer, and a hidden layer. And then you have a training set. And with that, you train the hidden layer. And then they have a test set. Then you can actually do the prediction for that test set. So that has been around for quite a long time. What has happened during the last 5 years is that the number and variety of different architecture has really exploded. So you have a traditional more addition, where you have more layers than the normal feed-forward network that has been quite used for chemogenomics and bioactivity prediction, like in a multitask setting. You have the convolutional network, which has been used a lot in image processing. It's very suitable for that. You have the autoencoder architecture where you basically transform it into a vector, then you transform it back again to a structure. And you have what we have worked most with, which is the recurrent neural network. And the difference between the recurrent neural network and the other architecture is actually in a recurrent neural network, you also learn sideways. You don't know, let's say, learn back and forth, but you will also sideways. And that makes it particularly suitable for strings, for speech, and so on, and for time series. So in those application domain, recurrent network have been really successful. And why are we doing it? And I think it's basically to be able to really explore the chemical space. So when you do hard-coded enumeration, then you can enumerate 10 power 10 or maybe 10 power 12 molecules, which is a significant number of molecules, but it's really a tiny, tiny part of the chemical space. And we can always argue how big the chemical space or the relevant chemical space is. There are a lot of estimation from 10 power 30 up to 10 power 80. So, but it's at least so big, so it can never really be enumerated. So you need to work with different type of applications. And I think why you're interested to be able to sample from the whole chemical space is a lot around scaffold hopping. If you just want to optimize a series, then when you're only moving around that, I think then you don't really need to have a method like this. But when you want to do scaffold hopping, then you really, yeah, you want to sample the whole chemical space. Uh, and so, so how do RNN or recurrent like really work? And I think that the key concept is what's called a conditional probability. So you have a training set. So say, as an example, is a text corpora that you train your network with, and then through conditional probability, it can, given a set of strings or a set of words, predict what will be the next one. So that's an example here. You have the three words, the grass is, and through the so say from the conditional probability, you know that it's much higher probability that the grass is green than the grass is pink. And that's really, I think, the gist of the method, that you have that. If you have generated a set of tokens, characters, then you have a probability distribution. What should the next one be? And that can be applied to chemistry as well. So if you have very simple molecules, you have C, the carbon, carbon, double bond. What is the probability for the next one? And then it will be a high probability the next one is actually an oxygen. Uh, because that's then basically have an aldehyde, which is of course a very common compound. And if we apply that on say to a structure, so a chemical structure you can basically describe in several different ways. You can describe it as a graph, which is a very natural way. You can describe it as a string, and there's a very popular language that called smiles. So this is an example of smiles. And then you have what's called, what you use in actually the R, and then you have a one hot encoding of the actually the smile strings. And usually you combine some of the characters. So CL is combined to one character because they will always, if the chlorine, they will always be together. So you do that to make it a bit easier to train. And then you need a prior to train on. And in the paper that I referred before that we published, where also actually the code is in GitHub if you'd like to try it out, we used the Campbell database, which is a public available database. And we used most of the database, 1.5 million compounds. We did the canonicalization. Usually you do that, so you describe each molecule with a unique structure. You don't need to do it, but it simplifies the training a bit. And then you have Campbell, you train to mates, and then you have a pre-trained network. So here's description of what actually happened. And then when you start, so your first character of the smiles, then you have a probability distribution what that character is, and that's in colored in green with high probability. Notice it's a logarithmic scale, so this is so it's a very big difference between the up here and up here. It's 10 or e up power 15. But you see that the most common one to start with is either carbon or an oxygen. So the carbon has the highest probability than oxygen. But you sample from that distribution. And then this time we selected an oxygen. Next time we select a carbon or another according to probability distribution. And then to the right, we will actually display the molecules. So you start with a carbon, and if you have a carbon, then you get through the conditional probability what the next character will be. And that could be, for instance, a carbon, but there's a very high propensity that it will be a double bond, because a carbonyl is very common. And then you select the double bond, and then you continue like that, and then you see different probabilities to the left and the molecule building up to the right. So this is actually, yeah, exactly how it does. It's the conditional probability that decides what the next character will be. And then it builds up a molecule that in most cases is not in the training set, but somehow overall have characteristics like the compounds in the training set. And that's what actually makes the method very attractive. And then we apply it on reinforcement learning. So we have the agent, and then we do the action, generate the molecule. We have a raw, active, good duplicate, synthetic, accessible, and then we update behavior. So we go around in a cycle. So there are also other way of, let's say, change behavior like transfer learning, but reinforcement learning is the one that we usually use most. And here's a short movies that we like to optimize structures that have similarity to celecoxib, similarity index of 0.7. So they should be reasonably similar, but not exactly as celecoxib. And then we see how it works. At the beginning, it starts to sample molecules, and it's more kind of randomly. It looks around in the chemical space to, yeah, check in different areas if there are some compounds that are similar to celecoxib. And then after a while, it actually start to find molecules. And then, at least for chemist eye, you can see that actually molecules are not identical to celecoxib because we said it's going to be similar. But you clearly can see that they, on average, have moved to be much similar. So that's basically how you given a specific scoring function, which is this time is similar to celecoxib, can actually get RNN through reinforcement learning to actually generate molecules that, yeah, that we like to have. So, this is just to quickly mention. I think it was mentioned before as well that we are working mainly with strings. You can give some argument that actually graph would work better, theoretical argument. I think it needs to be shown in practice as well that that's the case. But it's definitely something that we are looking into, and I think also others looking into, also given the number of papers that have been published around graph in the last 6 months. And then there have been some misconceptions about RNN generated molecules. One has been that the molecules are not diverse. Another is that the generated molecules are not synthetic feasible. And I think that has been answered. I'll come back also to diversity later. But clearly, the original paper from Marvin showed that you actually you generate diverse molecules. So that's only a preconception for people that have not actually used the method. But when it comes to synthetic feasibility, I think it is more subtle. But we have seen, and also was in this paper from Novartis, is that the synthetic accessibility of feasibility follows very much the prior that you're using. So if you train on simple molecules that have like an amide coupling, amide bond, then actually molecules that are generated are also synthetically feasible. If you would train your RNN on natural products that are difficult to synthesize, also the generated compounds will be difficult to synthesize. So I think that's a non-intuitive actually effect that the RNN also for more complex properties follow the distribution for the generated molecule, the same distribution as you have in the prior. And that's also one reason I think it's an attractive method. So then comes in, how do you evaluate algorithm? And for different way, different algorithms and different methods. And there are some standard ways that it usually report that. How many of the percent of the generated molecules are actually parsable by a smiles parser? With RNN, it's usually high, at least 95%, particularly if you use teachers forcing for training. For others, it might be lower. How many percent of the generated molecules are novel, not in the prior? It's usually also high. And how many of new generated molecules are unique, which are also high. But I will come back today, and then you can compare overall distribution between prior and the generated molecule. And also, Marvin has a paper out or preprint out about, so to say, comparing different algorithms. There have also been publications where actually they have synthesized generated molecule that have been predicted to be active, and they could actually validate it in the screen that has been published. So where we're coming from, as I said before, you can use these for two things: to optimize a series or to do scaffold hopping. Particularly if you like to do scaffold hopping, then you will actually assess if you're searching the real chemical space that you're interested in exhaustively, and you only sample that chemical space and not other parts. So that's basically what we've thinking about in the last few months. I have a PhD student that has been working on that. So that has been a collaboration with Jean-Louis Raymond's lab in Bern. So we are on the same European Union project, and we share a few PhD students that this work has been done by Joseph Wispel. So basically, we have in Jean-Louis Raymond's lab, they have created a database called GDB, where they have actually, through graph theory, generate all possible molecules. So there you basically have the ground truth. Given a certain size, this is the all molecules you have, and also applying some filter for that they are somewhat realistic. And that means that you can train the small set, and then you want to generate as much as possible of these blue molecules. You have the GDB, but then you can write all GDB molecules in various smiles. It's actually more strings that are okay to generate. You want to be within that. You don't want to generate, so to say, strings that are not valid smiles, or you don't want to generate actually valid smiles but are not represented within the GDB database. So that's, I think, I think for me, a very realistic test case or benchmark set. So how well your generative algorithm is actually working. So what we did, we got training with 1 million compound, which is basically 0.1% of the total database, and then we sampled 2 million. And then we can see what we get. And then we can see to the right first when we train the epochs. Then we can see how big part of the GDB so to say, we were generating in the 2 billion samples. And then we see we basically reach a maximum. So before, then it's, I would say, under-trained. So it generates quite a few molecules that are not part of GDB. And then after, say, 70 epochs, you start to overtrain, which means that you start to generate the training example much more frequently, or molecules close to the training example. So there is definitely a maximum of where you should actually train your RNN. And we can see that in the graph here as well, that the number of, of the 2 billion molecules sampled, 80% were in the GDB, and of them, 35 was unique, which corresponds to 70%, and around 20% were outside GDB 13. Of course, there's more detail in the paper. So the paper is actually not on arXiv, it's on ChemArchive, and it was published on ChemArchive yesterday. So if you're interested in details, you can go and read it. And we also have released the code for everyone else to be able to reproduce our data. So I think that this looks actually promising, and I think I'm actually very happy with this result. And I think actually smiles-based RNN, you can argue do a good job of actually sampling the chemical space. So what we did more, we was repeating the experiment 25 times to actually see if you would sample the whole GDB. We did once we sampled it for 70%, and then we repeated it 25%, and then if it would have been ideal, so all molecules would have the same probability, then it would correspond to a binomial distribution, which is in the blue. For average molecules, probably sampled 23 times or something like that. But we have a bit of a distribution. So actually, there is 0.5% that are not in any of the 25 runs, and it's really, and we show more in the paper, is actually how common or uncommon are the substrings in the smiles that you have, and we can basically see that the compounds. This is the probability of the compound. It's log likelihood, so the probability is the e and then power like -20 or -30. You can see there is a probability distribution, and those ones that are never sampled have significantly lower probability. I mean, you can actually construct quite complex ring system, even in a small database like EDB13, and those are basically never sampled. So there are reasons for that, and I think that's kind of when you have this conditional probability, that's quite logical. But it's published. All data is available from the GDB site, and also the code is available. If anyone would like to try out different type of algorithms here. And then, so to say, I think we have come quite far, both around generating molecules and also the synthesis prediction. So I always get the question, what is the bottleneck? And I think still the bottleneck is the activity prediction, particularly for a primer target, but also the selectivity. And then you need to think, what can you do to mitigate that? And of course, it's a lot dependent on the data. Clearly, what we see internally is that, for instance, we need to train with internal data. We can't only train with external public data. So data is usually the key. And of course, what we aim to do, and I think many others aim to do, is actually to combine the chemistry automation to actually be able to quicker to generate the data you need for your models. I think that probably is the key. Better descriptors, but we work internally with experimental descriptors derived from HTS fingerprint and so on, and that works quite well. But then you need to synthesize the molecules, of course, and have them. I can't do new machine learning algorithms. I think I need to speed up. Free energy calculations, I think, have some progress. There have been progress in speed. You need to work more with confidence estimation. I think work a lot more around benchmarking to actually understand different methods. And I don't know if anyone here is participating, but there's a new D3R competition going on at the moment. I think those competitions are very important because what has been seen is there's a quite big difference in accuracy between retrospective so to say calculations and when you do prospectively, you do some prediction blind, and the standard deviation they see in the blind prospective prediction are much higher than have been reported in literature for the retrospective. And let's see, and here's just an example of how actually we run the platform internally. So we generate molecules, and then we based on an internal database, and then we have reinforcement learning. So we generate the molecules, we score them, all type of desirability function, potency, argument, novelty, etc. We get back how good they are. That goes through the looping and reinforcement learning, and then we have a good set of compounds. The chemist is actually looking at them, and then we prioritize them for synthesis, both to find new scaffold, but also to optimize a current lead series. And then we try as much as possible combine it with the automation platform that we have constructed. So basically, which have three main parts. It's the chemistry part, the purification part, and the testing. So we aim use quite often cycle times for the DMTA cycle on the robot platform for 2 hours. So that's kind of, you get back data much quicker compared to, of course, the normal DMTA cycle. We talk maybe 4 to 6 weeks. And then just how we think it goes forward from augmented design, autonomous design, automated design, just quite a lot of how the car industry have actually evolved. I think the goal is maybe first not to create new drugs. I think it's to create new tool compounds that you can actually probe the biology. Because if you have a way to really create tool compounds fast, then we can, uh, let's say, approach TITV in a completely different way than we are doing now. And I think that should probably be a goal on the way to speed up the also last step around when you actually optimize your compound to be a drug. Here's a conclusion. You, uh, the slides will be published, so you can read it, but I think that's a repetition of what I've said. I just want to, because I only have 40 seconds left, go through the acknowledgements. So Thierry and Hongming, staff scientists, is my team, has really been essential here. But say there's a new poster coming in working on graph-based generation. Thomas Blask and Joseph, two PhD students through the BCAM network. We worked there together with Jürgen Bayer and Jean-Louis Raymond. We also have from the internal graduate program, Marcus and Danushka. Gary, that I think is somewhere in the audience, my line manager, has been very supportive. The discover safety method of police health building model. The respiratory disease have been very active and helped a lot, particularly Christian and Bangor. And then academic collaboration, also Marvin, when he was still at University of Minnesota. And also external funding for the Big Chem ITN, Innovative Training Network, where I have 6 PhD students spending 1.5 years in the lab, and they're all working on machine learning and push AI forward. Thanks for listening.